Okay, I think we can start. Once again, thank you very much for being here. This is going to be a webinar as you registered for the use of both Abaqus and Python. I'm going to start sharing my screen. I will start presenting some slides, but this will not be just a slide-based webinar where I'm going to open Abaqus and I'm going to show you my practice. So I hope this will be interesting for you. Just a quick heads up. You don't need to do, actually, I would suggest against doing exactly what I do with Abaqus, but rather watch what I'm doing. And maybe if you want to take notes, don't do it with Abaqus, because especially if you're not experienced with Abaqus, you may be left a bit behind. I think it's important you just understand what the tool can do, and then you can also repeat it. Also, our aim is to publish what we are doing today in YouTube. So this at some point will be also available for you later. Okay, so to start, as I mentioned, let me share my screen, and I'm going to start presenting, of course, first of all, the project FibReLoop. So FibReLoop is a Marie Curie training network, and what we want to do with FibReLoop is to boost the sustainability and the implementation of fiber-reinforced composites into a circular economic framework. It is a Marie Curie doctoral network, which means we have a lot of PhD students, especially in our project. We have 14 PhD students that are scattered across our industrial and academic partners, of course. They're all involved in a PhD doctoral program, so they're all studying and working hard for their PhD. Let me also thank a lot Mahesh Jedla, Alice Pagnanini, and Junaid Zubair for their help also in setting up this webinar. They are part of the outreach team of FibReLoop. So thank you to them three, but of course, thank you to all the candidates that are making FibReLoop a good project. FibReLoop is also composed, as I mentioned, we're scattered across Europe, and these are the universities and industries involved. So quite a strong European representation within the project, basically. About me, I think it's also useful for you to know who your teacher is, of course, because I just want to justify the fact that you'll spend the next hour listening to myself. I am assistant professor here at Politecnico di Milano. I teach one bachelor and one master degree level courses on finite element analysis. I also teach a laboratory course on destructive and non-destructive testing of composites. And I also organize a biannual PhD course with teachers from all across Europe about modeling of damaging and fatigue in composites. So yes, my main background is on composite materials, but I specialize a lot in the modeling of it, and of course it's numerical modeling with Abaqus, and this is why in my career I had to start also looking at not only maybe what you have heard you can do with Abaqus, that is the use of subroutines that are very advanced tools, but also Python scripting for Abaqus itself. About this webinar, what I want to do is give you a perspective about the use of Abaqus and Python, a perspective from a user point of view. What do I mean? There are a lot of very good courses on both Abaqus and Python, but of course, they really go deep into the scripting, into the Python grammar, and I want to give you the experience not of a person who is expert in teaching necessarily these things, but rather how I use these tools in my everyday research job, let's say. We will touch different level of complexity. complexities. So don't worry if, especially at the beginning, some of you may think, okay, this is quite obvious, quite trivial. I know already this stuff. We will get to the point in which this is more complex. Also, if you think that this is quite complex since the beginning, as I mentioned, it's okay. We're going to republish this in YouTube. So it will be for you also available later to study better. Also, I don't want to provide a sort of instruction list, but like I said, I want to show the potential from a user perspective. Also see, given the fact that some of my recent publications are based on the use of Python and Abaqus. We developed an algorithm I will talk later about. But this is, I really saw the potential of this tool and this approach to combining both Abaqus and Python together to really boost what you can do with Abaqus, basically. So let's dive in. This is what I tried to sort of categorize. You see, I have sort of defined 3 levels of difficulties. The first one is simple automation of everyday tasks, then make these tasks repetitive. And finally, what I think it really pushes the boundaries of what you can do with Abaqus is using Python to actually go inside input files and start modifying those actually. Before we start, actually, I think I just want to give you a trick that is, for me, one of the most important when using Python with Abaqus is basically the knowledge of 3 very important files that you have, simulation files that you have while you're doing your simulation. These files are the journal file, the recovery file, and the replay file. And we're going to see now why these are important, but for now, just know that these contain the Python instruction to anything you did in Abaqus. So they're very powerful. Let me start using Abaqus. Let me bring up the webinar in the other screen so I know that you're still there. Yes, it looks like you're still there. The first thing I want to do is actually directly go and open Abaqus. So I'm going to wait for it to open. Okay, and it's very important here. Again, this to a lot of you will seem trivial, but I want to start from the very basics. If I start now doing anything, this is already something I could lose. I could have lost at some point. So the first thing I strongly suggest to do is you go to File, Set Work Directory. And here you see that by default, Abaqus works somewhere. Usually it's the temp folder. Here, for example, in my case, is system32. But of course, this is not useful because you will just see this environment and you will not be able to go inside the actual list of files. So what I want to do is click here, select, and oops, sorry, from time to time, my Bluetooth receiver goes away. I have to restart it. Yes, I click here and then I look for the folder I want to use. For this webinar, I already prepared a special folder. It's this live folder here, actually 01. It's going to be the first example we're going to explore. And now, if I go into the 01 folder, it's still empty, but what I can do is I can save my model with, for example, 01 example. Oops, it's not working. Sorry, let me reconnect Bluetooth. Yep. Yeah, now it's working. 01 example 1. Okay. And now you see that I already created the CAE file, which I'm sure everyone knows how to use, but also this, the journal file. And this is one of the 3 very important files that I mentioned before. Now, the example we're going to have a look at as first one is this one. So it's just a very simple plate with a hole in it. And basically, these are the dimensions. And what we want to do let's say at some point I need to test, to simulate these plates with, for example, 10 different diameter size. The way to do it manually, this would be simply to go to create part, make a 2D planar part. Remember always to give meaningful names to anything in Abaqus. Continue. And then, especially when you plan to use Abaqus, my suggestion is to use commands in which dimensions, numbers are clearly defined. For example, I can use this command, create lines connected, and then click around somewhere. That would work. But if I use this, create lines rectangle, I can define the rectangle by the coordinates, the numerical coordinates of 2 points. In my case, these points will be 0, 0, so x0 and y0. And the other point, if this is 0, 0, will be, of course, 500, 200. So 500, 200. This is my square. Sorry, this is my plate, my rectangle, and this is done. Now, before I do anything and before I continue doing stuff, let's have a look at the folder. Look, this .rec file came up. This is the recovery file I was mentioning before. If I open it with a text editor like Notepad++, like I mentioned before, I can ask it to please use Python as language. And these are the Python instructions for what I just did. In the model 1, with a profile, I created a rectangle using 2 points, 0, 0, and 500, 200. And then from this sketch, I created the part. So you understand how powerful this is, because a very useful thing I can do now is create a new file and then simply copy and paste all of this. Now, this is why I wanted to stress that this is just a user-based experience, because of course you can study Python, you can study Abaqus to the level in which you know exactly how to use these commands. But I think this would make you more Abaqus and Python developer rather than actually users. So I think this, to me, is the best compromise as an approach for a person who has to use Abaqus, who knows Python, but also want to push a bit further what it can do with both. So I can save this file in the same folder, of course. I'm going to call it, I don't know, create geom for geometry. And this is the file that contains the instruction we just created. I want to show you one thing now. This is the file. Look what happens if I save. If I save, the recovery file disappeared. Why? Because its content went to the journal file. So this is how the journal, the recovery, and the replay file works together. The journal files contains all the instruction until you last saved. Recovery and replay, they contain the instruction since, actually from the last save on. And this is also very powerful. Why? Because I can paste one command at a time. For example, now that I know there is no recovery file, I can create a recovery file just with the instructions of the whole. This is how I'm going to create the whole, create cut extrude. I'm going to use create circle, center, and perimeter. And once again, center point is going to be 0, no, sorry, that's a mistake. Is going to be half of the length and half of the height. So 250, 100. So 250, 100. And then for the radius, let's start with, for example, a diameter of 100 millimeters. If I have a diameter of 100 millimeters, I can use this point here, which will have as coordinate 250 plus 50, so 300, and 100 as y coordinate. So this is going to be 300, 100. This is our circle. This is our hole. And look what happened, as I mentioned, a recovery file was created with only the instruction of the hole. I'm going to copy paste this here as well. I'm going to save. And now this has all the instructions that I want to create the hold plate I just wanted to create before. Where is the power in this? The power is that I can edit this file because, for example, I can write, maybe I'm going to zoom in just to make it clearer, but I can write, for example, L for length, and this is going to be 500 millimeter. The width, no, actually, the height is going to be, we said, 200 millimeter. And then the diameter of the hole, we said, let's start with 100. The next step would be to keep editing this file. So for example, I know that here, this becomes L and this becomes H. I know that here, this is the center of the circle that defines the hole. So this is going to be, the center will be L divided 2, whereas the y coordinate of the center will be H divided 2. And the second point will be L divided 2 plus the diameter divided 2. Here we're going to leave as the height divided 2. And now this script will create plates with these dimensions. And you see how easy it is, because, for example, I can even copy this and edit any dimension that I want, for example. So, for example, just to show you how it works, if I delete the plate I just created, I can go here, File, Run Script, and this is the command to run the Python codes. If I run the Python code with the instructions that I just pasted, here it is the plate we had before. Again, this is just a file. I can edit it. It's relatively, I would say, automatic, but we will see later how to make it even more automatic. What I thought would be interesting for later is, what if now I want to extract the load displacement curve, for example, from different ODBs? And this can be done similarly to what I just did for the post-processing part. So I'm going to actually create a job. I'm going to be a bit fast here. So I'm going to create a material, even if I'm a composite person. Just for simplicity, I'm going to create a steel section and assign the section to this material. Okay. Usual things in the assembly. Create a very simple step. For the load, what I want to do is, for example, here, create an encaster on the left edge, for example, and I'm going to prevent all displacement and rotation. And then, for example, I'm going to pull this other edge by, yes, 0.1 millimeters. Load the mesh. I'm going to use, for example, a 20 millimeters mesh. I'm going to mesh this. This is a horrible mesh, I'm aware of it, but for the sake of this webinar, it's okay. And let's just quickly create exercise, a job, and launch the simulation. Hopefully I didn't forget anything. We just wait for the simulation to be completed. In the meantime, know that if you already want to start, if you have questions while I explain, you feel free to just write them. Yes, so this is done. And of course, this is an example of results. Again, I will never trust these results because of course the mesh is really terrible here, but again, it's just for the sake of this webinar. So let's have a look at what happens happened here. Okay, here I have all the files once again. Of course, the simulation files this time, quite large, but let's have a look at this new file. Where is it? No, sorry, it's not there yet. So for example, one thing I would like to do is extract the reaction forces along X on the left edge. So I can do XY data, I double click here, ODB field output, continue, unique nodal. I want the reaction force in direction 1 for all the nodes that are on the left. Done, remember, because often I forget. Save as, and then this menu appears. If I sum them, click OK, what I have is basically the trend of the reaction force. Let's have a look at what happened here. So if I open the rec file, no, it's not here. Where is it? There should be RPY file. Yes, I'm missing the replay file for some reason. No. No. That's strange. Let me save. Oops, sorry. No, one thing I can do maybe is if I close and open it again. Yeah, RPY. Yeah, sometimes Abaqus is just. Okay, so let's have a look at the results. Yes, of course, now I have to do it again, but let's have a look at this new file. This is the replay file. Be careful about this file because unlike the recovery file, this contains really everything that you did, even change the visualization, for example. So for example, where is it? Sorry, here. Let's do it again what I did before. Double click on XY data, ODB field output, continue. I want nodal quantities that are reaction forces along 1, so along X. I'm going to select these nodes, done, and then I do save as. This menu appears again, and then sum. Okay, I close this, and then my suggestion is don't do anything else because, like I said, even if you zoom, now that zoom will appear in the replay file. So let's open and update the replay file, and what we did is here. Here we have to be a bit more careful. We're still going to create a new file, but remember that you need all of these from whatever import. These are the way Abaqus deals with Python, and it tells it, hey, open, actually use all the modules that are installed. I'm going to save this as output processing, not as text file, of course, but as, do I have it here? Otherwise, I'll change it later. Yeah, probably somewhere and I can see it. It doesn't matter. I will just save it like this and then I'll change this. I'll change it. Okay, so we have our new file from scratch. And then again, what we have to do is copy these last two objects. Okay, so this is what we have. Let me just quickly close it because I have to change its extension to a Python file, so .py. Yes. Let's have a look at it again. And now this will do what it says here. It will open this ODB and then extract the variable RF, reaction force, along the component one. It will add it and save it as, where is it? Yes, no, it will just save it basically. Okay, another thing we can do, of course, is XY data once again, ODB field output. I can extract the displacement along X of, for example, a single node like this one, because this is the same here because displacement was imposed. And here we have our displacement. Let's open again the replay file. Yes. Once again, let's copy this. This is just the me plotting, double clicking on that and plotting it. So this is just the bits we need. Okay. And for example, we can already try and do it. So if I delete this and I go back here, if I do file, run script from here, output, you see I already have the two data I want to do. Once again, what is the power in this? The power in this is that I can say to Abaqus, actually, you know what? The output file I need for now, yes, it is called 01 underscore x dot ODB. So that basically when you have to open something, you do this. Plus the output file. But maybe next time I want this file. Or actually, much better it would have been if I have this file, then the next file that I want to use is this one, where the diameter is 90 millimeters instead of 100. And I keep doing this and repeating this. I have now basically a file, an instruction file that does, with 2 clicks, file run script, what it does with a lot of many clicks, of course. So again, here I think is the simpler part of it. It's like I said, this is the part of automation of simple task. What if I've shown you the pre-processing and the post-processing? I think it's quite useful already. But I think that the best part starts to get when you try to automize, to make this much more automated. How can we do it? I'm going to do this. So I will copy only the CAE and the journal in this folder here. I'm going to close this Abaqus here and open it. Actually, I also need the file we created before. That is this one, create geometry. Okay, like I mentioned before, actually what I really want is to test different diameter sizes from 10 millimeters to 100 millimeters instead of 10. So as it is now, I can create 10 copies of this file. No, not this one, the previous one. Let me close a bit. Now it's too many things I have open. I can create many copies of this one and just changing all these inputs basically. Or I can do something different, that is the diameters are going to be defined like this. So range from 10 to 110, because unfortunately Python excludes the last bit, with a step of 10. So basically we're telling the diameter now is not a variable, but is a list of numbers, that is 10, 20, 30, and so on, until and excluded 110 with steps of 10. Then what I can do is I can indent all these instructions and repeat them for a generic diameter d in the vector diams. Now be careful because we need to no, sorry, this is not diams, it's just diam. Be careful about this. Of course, we need to change this one. This becomes just d. And there is actually another thing we need to be careful about, because if we now run this code, yes, it will try to create different parts, but all in the same model. So what we want to do here is something that is like diam, so diameter is, and then plus the string of d. So for example, if d is the first entity of this vector, so for example 10, it will make it into a string so that this becomes a string, so basically a text, and each model would be diameter is, for example, 10. Of course, we now have to be careful about changing all model ones into diameter is underscore whatever it is. Replace all. I save this. I think we don't need to change anything else because L and H are unchanged. Let's try to do file, run script, create geometry. If I click OK, of course, it's something is off. Let me see. Wait. Where is it? Yeah, debugging is not super nice usually when you do this stuff. Actually, let me see again. Where's the mistake? File, run script. Line 20. Diameter is the last string of D. That should be correct. Let me try one thing. Okay, let me try again. Sorry. Yeah, of course. I miss, of course, the model creation part. So how to do this? We can do this. We make sure we don't have a recovery file, and then I create just a new model. Double click on models. Okay. We now have the recovery file with the model creation. I copy this and then I paste it here. And the name of this model is going to be this one. Let me delete this. Now, if I run this model, this script, here we are. We have 10 models, all with, all with their increasing hole diameter. And then, of course, you see where the power is of this, because, I mean, why limit ourselves to just the diameter? No? Now that this is parameterized and it's automatic, we can go even further. We still have the rec file now. Let's go to model 1, our sort of reference model. I save so that the rec file disappear. And now I'm going to do basically everything I do for a simulation. So property. Yes, okay, no, actually here it's done already. Let me delete this material section and the section assignments. Let's do this. Wait, I'm going to restart from scratch. Actually, yes, okay, yes. Okay, property, yeah, no, here, sorry. Okay, so for example, again, let me save so that the rec file is deleted. Again, here I call this steel, mechanical statistic elastic, once again, 210, 123, 0.33. Section 1, assign this section, done, okay. And once again, let's open the rec file, yes, and let's add all of this inside the for loop. Always remember that it's always very useful for your colleagues to comment. This is create material and section and assign it. And so on, basically, because then what we do is in the assembly, we bring this back. Okay, we open the rec file, and this is the last part. This is the comment assembly line. That's actually nice. Assembly, the step creation, once again, continue. Okay, and then let's see what we have here. And this is basically it. Okay, I'm not going to continue because I guess you got the point. But what is very interesting, I think, at some point is also that you can even do this. Double click on job for diameter is 10. I call this 0, 1, for example, job of diameter 10. Okay. And then if I open the recovery file, here it is. Here is the job creation. Sorry, we need to remember to respect the indentation with Python always. But this is the job creation command for Abaqus. So the model that we're going to use, of course, remember to change this into the parameterized model name. This is also model, this one. And this I can call 01 job of diameter plus the string of the current diameter. Here I can even define, this is very interesting actually, the number of CPUs to be used in the simulation. The number of GPU, you have a lot of commands that you can exploit. And this, of course, will create, in this case, 10 models with all the material and all the assembly defined, and it will create 10 jobs. This, I think, is already start to be very useful because you can imagine, even for what we did before with the visualization. No, I don't have it here because it's the other folder. But with the visualization, we said, okay, actually, let me open it. Now this is a command to do that thing. So I can edit it when I want and launch it every time I need. Or once again, I can put all of this into a parameterized for loop. So to tell Abaqus, okay, you know what? Look for all the files with the ODB extension and run this command for all of them. Of course, here you have to be very careful about the names, because then if you call everything, I don't know, displacement 1, then Abaqus will say, okay, I already have it like this. So you have to be careful with the names. But this is very powerful, I think. And then finally, this is the second part. The second level, I would say, of automation, and I think this is already quite useful because, yes, level 1, I think, allows you to sort of create tasks, let's say, create files that then you, how to say, sort of instruction file that then you can launch when you need. But this level 2 is true automation, I think. Basically, this repetitive instruction is inserted in a for loop and launched for all the files, all the simulation, anything you need, basically. The last bit is what I think it's a bit, it's quite more complicated than this. And it regards the fact that we have input files and that you can use actually Python to edit input files. First of all, for those of you who don't know yet, you see that we have all these files inside the folder that that we used, and these files are all, I think, very important to more or less know if you plan to really exploit Abaqus at its maximum. The input file I'm referring to is this one, the .imp. Let's open it and see what's inside. Oops. Here basically is your entire simulation. This is your entire simulation made in a script file so that Abaqus can read and launch. For example, here I have the nodes. For example, all the node number, node 1, node 2, node 3, with coordinate x and y. These are the nodes. If you go down, these are all the elements. For example, these are the elements. Element 9 is connected to node 307, 308, 1, and 2. And then we even have the assembly, the materials, boundary conditions, and so on. Now, I'm going to open a file that was already created because I see we're running a bit out of time, but I think it still conveys the message. So this is a file I created before. It's a simple, very easy plate. It's bent. So here we have an encaster. And here I will show you. And here we have in this surface a sort of unitary pressure. Now, the way I defined the encaster is by the set of nodes. What does it mean? Here in the assembly, I can say, you see it, set fix. I defined, actually I will do it again, set, create a set of nodes. Let's call it fix2, for example. Continue. Let's just go in one of the useful views. For example, in here, I can select all these nodes. Done. And now this is the set of all the nodes that I want to be encastered. And in fact, for example, I can do encaster 2. I will not launch the simulation because otherwise it's going to complain. Continue. Here in sets, I can say that I want the boundary condition of encaster applied to all these nodes. Why I'm using this now instead of the standard just click on the surface? Because look at this, I have created a job and I can do right click, write input instead of just launching the simulation. Write input creates the input, this one, the input file, without launching it. It just creates the file that you need. Let's open it and see what's inside. As always, all the nodes, all the elements, and finally, I see that the encaster boundary condition is applied to the fix set. And where is the fix set defined? Here. Node set called fix, and these are all the nodes that are inside that, that set. Now, let's say that I want to do something, for example. Let's say that I want to encaster, instead of this element, sorry, these nodes, I want to encaster the nodes. Let's get the mesh back. I want to change the nodes that are encastered. For example, I would like to constrain these nodes or these nodes. So what I did, and again, I don't want to do it live because it takes a lot of time. is to create a Python code that selects all the nodes with a certain Z coordinate. I'm going to show this by launching this in Python itself. I'm going to use Spider. Yes, you see I've commented all the lines that are related to Abaqus because of course Python doesn't know them. And what I do, I'm going to launch this. These are just defined functions, so let's keep them for now. The actual code starts here. Input file, 0, 1 bending. Now, I told Python, open this file and read all the lines. 0 input, I call it. This contains now all the lines of the input file. Basically, these are the lines of my input file. This is very useful. Why? Because then I created, okay, these are the new nodes. And with this function, I can read all these nodes and select the ones with a Z coordinate of, for example, 20. For example, this one, and so on and so on. So the list is called nodes, and you see these are all the nodes. And from the initial list of nodes, I grouped all the ones with a Z target, for example, of 20. Then, of course, I have to put these nodes where? Here, into this new, where the node set fix is defined. How do I do this? First, I have to look for this line. So I told Python, okay, search for the line that starts with nset equal fix. That is the Abaqus syntax, Abaqus grammar, basically. Then what I did is, first, with this bit of code, I sort of made the, I arranged all these nodes into the into the Abaqus grammar. What does it mean? I told basically Python, okay, write a string that does this. You have 16 nodes here, and then you go to the next line, and then 16 nodes again, next line, 16 nodes again, and so on and so on. But in the end, what I have is basically this one. You see, one line with the first 16 nodes, the second line with the second 16 nodes, third and fourth. And then I will just create this new input that is a similar file to the 0 input one. Where is it? New input. It's exactly the same. And in fact, it is the same as the 0 input from the first line up to this line here. So from here before, it's all the same. Then I told them, okay, I told Python, instead of using this, paste the set, the string, the new set of nodes, and then continue from 5 lines later, that is from here, all the way down. Of course, now I didn't include it here in Python directly. Wait, it's not okay. Oh, it's not going down for some reason. Yes, but then I can create a new input with this command. And I can create a new file called new input.imp. And this is exactly the same as before, except that here I have the new set of nodes. What's next to be done? If I go to Abaqus, I miss one command. And the one command that I'm missing is the following. Create a new job, not from a model, but from an input file. Which input file? The new input I just created. Okay, Yes, this of course exists. So I'm going to, no, it's -1. It's okay. Continue. Okay. And then just like before, I open my recovery file and I see the command to do what I just did. This is input file name. This is the input that I used to create the new job called like this. And then I can include, sorry, let me open it from here. I can include also submit this job. And actually, these other 4 lines are lines that tell Abaqus, okay, wait for it to finish. This, honestly, I just find it online to include it in my code. And once again, you understand the power of this to create an input file, a job based on this input file, and to launch this simulation, wait for it. And this is what we did here. But actually, if you think about it, what I said before to include all of this in a for loop can be extended to here. And so you can include this in a for loop, create a new input file, submit it, wait for it to continue. You can include a post-processing phase in which you extract the results, you prepare a new input file based on these results, and you launch a new simulation, wait for its completion, and so on and so on. And this is exactly what we did here. Let me go back to my slides. Oops. No, sorry. I may click the wrong button. Okay, yeah, swap. This is the correct one. This is what we did here. And like I mentioned, let me just briefly present it, rather than from an Abaqus perspective, not really from a composite perspective. This was a work we did with the simulation of delamination under fatigue, and you have to imagine that you have these two plates, let's say, that are bonding to each other, and they're subjected to this load. So it's a peeling load, basically. And at the beginning, you have the bonded surface that is something like this. Now, with Python, we prepared the geometry and everything. And then what we did is we launched a first simulation. Again, this is a fatigue analysis. So to this simulation, we associated this first simulation with a number of cycles equals to 1. For those of you familiar with clock propagation, you know that Paris law is what determines the speed of advancement. But in general, what we wanted to just do is extract the results of the previous simulation, use it inside Python to do some calculation, and then to launch the new analysis with the new input file associated to a new cycle count and with a new bonded surface. This was easy, and this is why I used the example of the node set, because if you use a technique called virtual crack closure technique, VCCT, you actually have to work with sets of nodes. And this was very efficient, very easy to use with Python and with input file, playing around with input and with input files in Python. And then you can launch this until you reach the number of cycles requested, or until, for example, all the surfaces delaminated. We found that this was super easy to implement, especially if you compare it to what was the state of the art back then. I know that some of you are familiar with Fortran and with subroutine, but I'm pretty sure that those familiar with this, of course, are also familiar with how difficult it is even to install and connect together Fortran and Abaqus. It is much more versatile now because, again, the calculation of the speed of propagation are done in Python, not in Abaqus. And then it just becomes addition and subtraction, very easy. It led to very good accuracy, but this was our main selling point. We had drastically improved computational efficiency with respect to any other method that we observe, because what you do is, instead of launching one single but very complex fatigue simulation, you launch many very easy static simulations. By the way, this is an algorithm that we developed for fatigue and delamination of it, but of course, feel free to think about something else, even, I don't know, CFD or something like that. It would be very interesting. Of course, I'm specialized in composites, so I don't know other potential application field, but if you see potential for this idea, I think it's worth exploring, definitely. That's the end of the webinar. I think it's 55 minutes we covered. I think it was okay. Let me conclude by advertising the fact that as of today, we officially launched the registration of our FibReLoop school. It will be held at the University of Twente. So I think it's a very excellent opportunity to learn from quite experienced professionals in the field, both from academia and industry. It will be held in mid-April, let's say. I will put the links for the school now. Maybe you see the prices are very reasonable, I think, for PhD students. 3 days full of lectures, and then you will also get the chance to meet both the lecturers and the FibReLoop doctoral candidates, which are very nice people. And of course, this concludes the part where I talk. At least I start talking. And then, of course, if you want to have questions, feel free to ask. There is a thank you. I'm going to publish it. Okay, I see a question already. Let me see, because wait. Okay, no, first I'm going to read it, then it's the first time we use Teams for webinars. So first I'm going to read the question out loud, and then I'm going to publish it because I'm afraid that maybe it goes somewhere and I cannot find it anymore. Thanks for your explanation. I have a question. Is Abaqus capable of modeling the cracking mechanisms that occur in cutting tools under machining conditions? Let's try and publish it and see what happens. Yes, it's there. So again, I specialize in composite materials, so I don't have a 100% sure answer, of course. I guess that would be possible. I think the usual suggestion as a PhD supervisor I can give is check the literature. I would definitely think that if you want to further boost what you can do with Abaqus, if the answer turns out to be no, you cannot do that, but then you're a PhD student, so you still want to do it, the usual approach would be look for subroutines. For example, I know that there are subroutines, Fortran subroutines, dedicated to contacts, element deletion. So the combination of them could be useful. But again, I think that now we have this new tool that is the use of Python also instead or together also with Fortran subroutines. So my suggestion is to explore both the literature, but also what can be done with both Fortran and Python. Again, so far, Fortran was the only go-to. I really feel Python has a lot of potential. So yes, check the subroutines, but also check and try to think how you could implement this with Python, because it's really, really powerful. Just thank you. Yes, people thanking. I'm going to wait a bit more for other questions. In the meantime, I see some people leaving, so let me just thank everyone who attended the webinar. It was very nice doing this. Again, we're going to publish it, so I think it's for you, if you want to see it again, this is a good opportunity. And again, check the FibReLoop website, and but I hope I will see some of you at the school. There is another question. Is there a way Python can be used to replace Fortran with for subroutines? This is what I said. I think we did it. We did it with the fatigue ones. The standard practice before that in Delamination in composites was to use user elements, so UL, it's the subroutine dedicated to elements that replaced cohesive elements. The way we did it is with Python. So there's no way with no need to use Fortran. Of course, there is not a, how to say, standard way, I would say. You have to find a sort of ingenious way to do it, probably case by case. But overall, I would say that a lot of the things that can be done with Fortran, if you put your heads into it, can also be done with Python. Can Abaqus be, oh, sorry, maybe I'm missing some of the question. Thanks for a nice presentation, thank you. Can we build our VE model of recycled fiber and matrix using Python and Abaqus? Definitely, 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 yes. This is what I was saying. I think this is the pre-processing side of this webinar, I think. You can try and sort of implement the sort of statistical generation of fibers in Python, do all your calculations in Python, and then create, based on your calculation, the input file, or even just generate the command to use it in the CAE. I will even go further. I have experience also with using together Python and Fortran to sort of prepare, use Python to prepare simulations that then use subroutines, or you can even use MATLAB and Python together to create the input file. We have also experience with that. There is a very good PhD student of us that is doing it for work on foot prosthesis. I have to be honest, I don't know if he combined MATLAB and Python because he was not too sure on Python, so and he was more confident on MATLAB, so he combined them. But in general, what I would say is that you can even do that. So combine, if something is missing in Python, you can combine the things and create a sort of superscript that launches simulation automatically. We have also a question, can Abaqus be useful for fabric-based polymer composites modeling, particularly for drop weight impact testing and automate some fiber volume fraction results? That is very specific, particularly drop weight impact testing. I would say yes. Again, the difficulty with Python, but I would argue it's the same with user subroutines with Fortran, is that it's not a button. It's not a button. You just click and it does it. You have to find your ingenious way to do what you want to do with Python or with Fortran instead of the standard Abaqus tools that you learn in at the beginning, I would say. For sure, I would say that automating some results analysis is something that Python is there for that. I don't know what you mean exactly with the modeling drop weight impact, if the load part or the creation of the input file, but I would say that probably you can find an ingenious way to use Python for this. Oops, sorry, I forgot to finish the question. So wait, the question was to replace Fortran. I wanted to know in perspective of the constitutive model. That's interesting, actually. That's a good question. So I'm going to rephrase the question for those of you who are not familiar with this. The most common subroutines, usually, at least the ones I've seen more, are UMAT, user material, and UL, user element. These are called by Abaqus element per element, especially the UMAT, to implement a new material model. Now, can you do this with Python? It's not something that I have looked directly into it, in the sense that constitutive models probably still needs to be implemented by Abaqus, which means that if you have a progressive law, for example, damage involved, so a constitutive law that depends on the applied conditions, then I would say yes, you still need Fortran. If, for example, you can use Python analytically to create a stress strain curve, then perhaps you can feed that stress strain curve to Abaqus without going through Fortran. One other thing that I think it would be interesting is to use Python to create the Fortran subroutine and the Fortran material model, or even to prepare input for the Fortran material model. In my experience, using Python for automating simulation is powerful, but when it comes to meshing, it can be tricky. I agree. Can you please share any suggestion to this? Yes, I agree. Especially because we're a lot used to click. For example, I want to mesh this part. Okay, I click here, and this is it's difficult to create a command that says click. Of course, click here. This said, I think that you can find some ways to improve the mesh. For example, one thing we did, especially in this case, was to sort of create partitions with Python so that the mesh generation is easier and more immediate using the automatic meshing of Abaqus. I would push it even further, but I have not done it, and I realize it's super difficult and hard. But if you can maybe think of a way to generate the mesh directly in Python and then just copy the number of nodes with their coordinates in the input file, that would be very amazing, I think. But again, I understand it's quite difficult. Let me see. Maybe I missed one. Yes, I'm trying to develop a script for automating the application of periodic boundary conditions for my specific simulation. Would you suggest to act on the input or create a script through the journal as you showed? So honestly, acting on the input, it really depends. It really makes sense when you are limited by what the CAE, the Abaqus environment, can do. So if you know exactly your boundary conditions, where they're applied, and there's, let's say, what they are exactly, then I guess you can try to understand how they're written in the input file and then just ignore completely the boundary condition generation through the CAE and just write Python code that does it and then paste it in the correct line. For the rest, perhaps if you can find a way to do it with the journal, it's also worth investigating. I would think that it's easier and it takes less time going through the journal rather than going through the input. So my approach would be, let's try with the journal. Let's invest some time to try and see if I can do it. Just because I think that in a week, I hope, you will be able to answer the question, can you do it with the journal? If the answer, not that you do it in 1 week, but at least that you understand that yes, it's possible, no, it's not possible. So perhaps it might be worth investing some time in also looking at that. But again, if you see that the working and acting directly on the input, if you know already how the input should look like, then definitely go for the input. This I read. Can we integrate artificial neural network based regression modeling optimization algorithms like evolutionary algorithms with Abaqus and Python? Maybe we can directly achieve optimum solution by using one button for complex. So I'm not really expert on machine learning techniques. Definitely, I would say that combining Python, which is an analytical tool in the end, the way it's used here, can lead to some optimization. Actually, we did some optimization on the food processes I was mentioning before, simply, but let's say it was a tentative optimization, because what we did is new geometry, launch the simulation, evaluate the results. If the results are better, then keep applying that geometry modification and launching simulation until we hit the minimum. but using machine learning techniques, honestly, it's difficult to answer for me. Also because I'm not a big fan of machine learning techniques in my research field, of course, not in everyone. I deal mostly with physics-based modeling, so kind of circumventing physics is not something I'm a big fan of, let's say. Thanks, nice and useful webinar. Thank you for attending. I think I should have answered all the questions. I don't think I skipped one. If I did, please ask again. Oh, there's another one. Thanks, Luca. Really educated. Probably involve Python script into the adaptive mesh. Yes, I'm good. Yes. So involve Python scripting to implement adaptive meshing refinement for friction stir welding simulations in Abaqus to automate the creation of remeshing rules for complex configurations. I agree. Remeshing is something we are also looking into. The work of the Delamination modeling is something that I would say this is very promising, because so far remeshing is awful, because ideally there is a person that launches a first simulation, extract the results, and then says, okay, now I have to remesh it. Maybe here I see the results. So of course, remeshing from a simulation to the other, it takes huge amount of time. But actually, if you just automatically do it in Python, then nobody cares. You just launch it on a Monday morning, and then maybe on Friday afternoon you have everything you need, and then okay, the weekend you relax, but next week you see all the results. This can be a possibility. Definitely, remeshing is something that is very powerful with this Python and Abaqus combination. Will you open an online course directly focused on this webinar subject? Not sure what you mean, but what I will do is I'm not going to do another course on this, but I will. We're recording this, so I will the recording I will publish. We will publish it on YouTube on the FibReLoop YouTube account, so that you see it's available for everyone later, basically. Still have something like 13 minutes. Thanks for the webinar. Thank you for attending. Of course, I wrote it in the slides, but this is a Marie Curie project, so it's publicly funded by the European Union. So if you are in the EU working and paying taxes, that's also thanks to you that this is happening. Thanks again. Okay, I think we have answered all questions. Yeah, I guess that's mostly it. Thank you very much for attending this. We have more stuff going on with FibReLoop, but again, check the website. Really encourage you to attend the school, because when I was a PhD, I attended a Marie Curie school, and it was a huge opportunity to really meet the teachers bar, but also your colleagues, basically, and it was an excellent opportunity. Yes, thanks. We are reminded also of our YouTube account. It's posted on the chat. If you follow us on LinkedIn, we will for sure post advertise when we will publish this on YouTube, and every other major news, like the school that we did or any other publication that we get from there. Another question in the meantime: can we use hybrid element formulation for visco hyperelastic material? As I use explicit simulation, the available elements are causing submission. Can we do it in Python? That's a good question. I don't know what the issues that you're facing are, but I know that when you dug deep, especially with hybrid elements, Python can do many things. Actually, sorry, not Python. Abaqus can do more things than the Abaqus CA can do. So if you go on the guide, on the Abaqus documentation, you will see, for example, Abaqus can do all of this. To do it in the CAE, this is the, I don't know, the buttons to be pressed. To do it in the input file, this is the line of code. Sometimes that part of the CAE with the buttons is not available, so you only have the input file. So with Python, you can sort of create a command to say, okay, instead of launching the simulation, just write the input file, then you run the Python script that adds the lines you need, and then you launch the simulation. So perhaps this is a path worth exploring. Yes, again, we have YouTube, LinkedIn, and website in our chat. Yes, I think that's it for everyone. Once again, thank you very much, and I will see you around in Europe, I guess, with our FibReLoop activities. Thank you very much. See you. Bye-bye.